Hello, everybody. Welcome back to DeepRob for Lecture 6. In today's lecture, we're going to be talking about the backpropagation algorithm, which will be useful now for training our more complex neural networks that we're going to start looking at. And in particular, it'll be useful for, and really required for, implementation of the learning algorithms, the stochastic gradient descent and ADAM and some of those other learning algorithms that we looked at in the past lectures. So before we get started with the backpropagation content, I think just one administrative note today, which is just a reminder about Project 1. So the deadline is coming up this Thursday at midnight. So if you're having issues with the autograder, let the course staff know. Quiz 2 was today, so the deadline for that was just before lecture, so hopefully Quiz 2 worked out well. I didn't get a flurry of emails, so I take that as a good sign. Our next quiz is going to be on Thursday, so that'll open Thursday morning at 7 a.m. So heads up about that. And we started putting the quiz schedule up on the calendar on the website, so you can have at least a week heads up for future quizzes. So for example, both lectures next week, we'll have a quiz. Okay, so with that, that's all of the administrative updates. I'll just pause for a second to see if anyone has anything that they think is worth raising. Yeah. Yeah, thanks for, so the question was, are there no more office hours on Tuesdays? So the research associate, Huiji, he had to move his office hours only for this week, so he had 2 office hours yesterday. So on the homepage or the staff page, we'll start listing the weekly schedule. It won't change much. That was just I think there was a doctor's appointment. There was some reason why he had to move his hours. In general, they'll stay constant with what they were posted at the start of the semester, but if there's a week-by-week change, we'll have it listed on that homepage of the website. So for the rest of this week, the office hours are the standard hours. Okay. So getting into to sort of today's content. So briefly, I just want to recap what we were looking at in some of the past lectures. So in particular, in the last lecture, we saw how neural networks have a set of desirable properties for the purposes of our image classifiers or our robot perception algorithms. And in particular, what they will allow us to do is learn a feature transformation from our original input image and kind of pixel space into some latent space, some hidden space, which can make classification much more effective for nonlinear classification problems. And in addition to that, what we saw is that the kind of power from this is that it'll move from having sort of the performance that we would expect from a linear classifier, where we're constrained to one template per class, into now these neural network representations, which might have sort of many templates that it can use for its classification performance, and also just in general, it'll have higher accuracy on benchmarks. The challenge, though, that we saw was in terms of how to train these networks, because the loss functions for neural networks is non-convex, we're forced to use gradient descent algorithms or variants of gradient descent algorithms in order to train these to perform classification. And the key caveat with that, though, was before we could actually implement stochastic gradient descent, we have to define what the gradient of our loss function is with respect to the weights of our particular neural network. And so we left off last lecture with this really kind of daunting question, which is if we're given some definition of a classifier. So on this slide, for example, we're showing the score function from some one-layer linear classifier. So this score S. And then if we define some loss, so in this case, for example, we're using the SVM hinge loss, how it is we can actually perform gradient descent will depend on our ability to actually express the gradient of the loss with respect to all of the parameters of our network. So in this case, what we would need to actually implement if we were going to start training our classifier is we would have to define how it is you can have what the partial derivative of the loss with respect to weight 1 is, the partial derivative of the loss with respect to weight 2, with respect to the bias 1 and bias 2. And so this is a big kind of challenge, and probably what you're starting to run into as you implement Project 1, or if you've already finished Project 1, is that if you just are writing this gradient out on paper, it's really challenging to do. And in particular, it's really challenging to do correctly, right? So the issue with sort of this initial, what we might call a naive approach in comparison to some of the techniques that we'll look at today, is it's very, very tedious to actually hand derive for these multivariable vector-valued functions what the gradient with respect to all of the parameters is for some given loss, right? So it would require a lot of paper, a lot of scratch work to actually to write out by hand. That's one issue with this approach. The second issue is that if you decide to change your classifier, right? So if you decide to maybe move from the SVM loss function to the softmax loss function, you all of a sudden have to rederive all of those gradients by hand once again, right? And in addition, though, even if you make small changes, like you change maybe how many total weight parameters there are in your linear classifier, or you decide to include maybe a different nonlinear activation function within your network, all of those changes are going to require then that you rederive all of the gradients by hand. And so that's really, really expensive to do. And it's not going to be feasible as we move to larger and larger scale neural networks, right? With these relatively simple SVM and softmax classifiers, it's something that we could do. So you've now had experience with that on project 1. But when we start moving to like convolutional neural networks, or we start adding dropout or batch normalization or some of these more complex layers within our networks, this approach is simply not going to scale. And so a better idea, which is what we're going to focus today's lecture on, is using an algorithm which is called backpropagation. And so the core data structure that's going to be used by backpropagation is what's called a computational graph. And so the basic idea is if we could potentially represent some algebraic function, like the operations that go into one of our classifiers, as a graph data structure, then maybe it would be possible to define a graph-based algorithm that could operate on that graph data structure in an efficient way to automatically derive those gradients for us. So that if we decide to change the computational graph data structure, the algorithm that'll compute all of the gradients doesn't have to change. So sort of like the hard part will hopefully be handled for us as long as we can set up this computational graph correctly. So to kind of put that in more concrete terms, if we were to represent our SVM linear classifier as a computational graph, this might be one representation that we could use. So you can see that we have our inputs to our classifier would be our, let's say, our vector of images x, and then we have some learned weight parameter or some parameter matrix W which we're going to hope to learn. So the score of that is produced by the matrix multiplication, let's say, between the weight matrix and the image vector. So this node in the graph represents the algebraic expression, which is that linear matrix vector multiplication. So every node within a computational graph is ultimately going to be representing one particular algebraic operation. And then the different edges represent some transfer of data between the algebraic operations that we're trying to describe. So in the case of maybe setting up a training pipeline for this SVM classifier, once you've calculated your scores, you would pass those scores to your hinge loss in addition to the correct labels, but for the sake of clarity, we're not showing the labels on this slide. So this node here, this hinge loss, is what's used to represent this overall algebraic expression, right, which is what you've implemented in project 1 or are working on. At that point, then, you could also start to describe other operations which you might want to use within your training pipeline in this computational graph. So if you have some regularization term, you could describe that as an algebraic operation, whether it's L1 regularization or L2, which will take as input just the weight matrix W and not the input images X. And then our total loss, which we looked at, I think, 2 lectures ago, then would be the summation of both the data loss, which comes from the hinge loss here, and also this regularization term, which comes from our, let's say, L1 or L2 regularizer from that preceding node. And then that would set up your sort of final total loss for your training pipeline. So you can see that this graphical representation is an abstraction of the actual algebraic operations which your computation would be performing if you were to try and define the loss for some given parameter vector or parameter matrix W and some given input image vector X. So once again, so just to sort of reiterate, the motivation for setting up these computational graphs is that using them as a data structure, we can now start to try and think about an algorithm that would automatically derive what the gradient of our parameter vector is W with respect to our final output loss L, such that, and kind of like the hopeful property of that algorithm is that if we decide to change the computational graph structure, like maybe we decide to swap out the loss function or maybe have some additional algebraic expressions before computing the loss, the underlying algorithm which will compute the gradient doesn't have to change, and just the computational graph structure does have to change. And so once again, so sort of to look at like a more kind of relatable example of why this is going to be like a core motivation for us, is if we were to start thinking about kind of more state-of-the-art neural networks. So for example, this AlexNet, which we talked about a little bit in discussion on Friday, which was the winner of the 2012 ImageNet Challenge, it's much more complex than the linear classifiers that we've been looking at, right? So it takes in an image. In this case, actually, it takes in a very large image. So it's like, I think it's 224 pixels, or roughly on the order of 224 pixels square, right? So it's bigger than the images that we've been working with so far. So that's going to add some complexity if we tried to hand derive the gradients. But in addition, then, it's a deeper network. So I think in total there's like 8 layers of learnable parameters. And then you have nonlinear activation functions. Between those layers, you have like batch normalization, dropout, some of those other complex techniques, which we'll look at in some of the upcoming lectures, before you, at the very end of the network, define your loss for your image classification task. And so if we were to try and set up a computational graph for this network, there should be some desirable properties there, as opposed to hand deriving by hand what all the gradients are for this approach. And indeed, the original authors of this paper and of this network, they did not hand derive the gradients. They used a computational graph. Okay, so let's now look at an example of how we could use this idea of a computational graph data structure to calculate gradients and move towards defining an algorithm that will start to calculate the gradients for us. So what we'll do is we'll look at a particular algebraic expression, so the one that's shown on this slide as this function f. So we'll look at in algebraic notation here on the left, and then on the right-hand side, we have this computational graph, this image of a computational graph, which is equivalent to this algebraic expression. And what we'll do is we'll step through the kind of like the core operations that go into backpropagation, but in this specific example. And then later on in lecture, we'll start to talk about how this specific example and the core operations that we're performing in backpropagation will start to generalize beyond this instance of a graph. So the first thing to sort of consider when we consider this algebraic expression is what are the inputs and what are the outputs. So for this function f, you can see that there's 3 inputs, a scalar x, a scalar value y, and a scalar value z. And then the final output of this function is going to be the sum of x plus y, and the result of that then multiplied by z. So now if we turn to the computational graph and we look at what we have represented, you can see that our 3 inputs x, y, and z are shown on the left-hand side of the graph. The intermediate value, which is the summation of x and y, we're going to call this intermediate value q, is where my cursor is. And then the final output of the function is the result of taking that intermediate value q, which was x plus y, and multiplying it by the other input value z to arrive at the final output. So that's the way you should read these computational graphs, is sort of from left to right, where every node within the graph represents some algebraic expression operating on some either intermediate variable or some original input variable. So the other thing that's kind of important to think about with computational graphs is we're not going to treat the backpropagation algorithm as a symbolic, as a manipulator of like symbolic symbols. So instead what we're going to do is we're always going to instantiate the input values with actual data elements. So with actual either integer values in this case or floating point numbers. And then same with all the intermediate and output variables. And the reason why we do that with backpropagation is because we're always using it in the context of training a neural network where we actually have instantiated images and parameters, and then also some defined loss which we want to try and minimize. So in this case, let's work through the 2 core steps of backpropagation, which is going to be first a forward pass and then a backward pass, using the values for x, y, and z shown on this slide. So we'll say that x will take on some value, -2. So you see we'll draw -2 up where the x input is. Y will take on the integer value of 5, and z will take on the value of -4. So given these kind of instantiated values for x, y, and z, let's now work through the forward pass of this function. So, so the first thing that backpropagation does is actually just kind of move forward from left to right through the computational graph, calculate all the intermediate variables, and then finally the output variable. So you can see here that the intermediate variable q which was x plus y. So in this case, -2 plus 5 is +3. So first backpropagation stores that +3 value into the intermediate variable q. Then it computes the final output value f as 3 multiplied by z, which was -4. And so 3 multiplied by -4 is -12. So we've computed now the first step of backpropagation, which is just computing the full output value of our function. The second step then and this is really like the core then of what we wanted, is backpropagation will compute the derivative of the output of the function with respect to all of the intermediate and then original variables within the computational graph. So in this case, what that means is backpropagation will calculate the partial derivative of f with respect to x, with respect to y, and with respect to z, but also it'll compute the partial derivative of f with respect to that intermediate value q. So for the purposes of like, if we were to try and like minimize, let's say, this function, so we were going to change x, y, and z using these three gradients down here, we might not care about the intermediate value of df dq. But for the purposes of calculating these intermediate these final gradients, it's very useful to have the gradient with respect to that intermediate variable q, which we'll see now when we start to step backward. Okay, so given that these are the derivatives that we want, let's start looking at how it is we can do this. So the first thing we can do is ask, what is the derivative of the output of this function with respect to itself? So let's see. Does anyone want to sort of put forward a guess of what they think the df with respect to df would be in this case? It's not a trick question. 1. Yeah, exactly. So this we can, what we'll call this moving forward is our base case. So this is how backpropagation will always start. We'll always start by setting up just what is the partial derivative of the output of some function with respect to that function or the output of that function. And so it's always going to be 1. And the reason why that's useful is now what we'll start to do with backpropagation is step backward and we'll apply the chain rule from calculus to calculate the partial derivatives with respect to the intermediate variables. So let's say in this case now that we've got first our base case calculated, and let's step backward and now let's look at how can we calculate the partial derivative of the output of this function with respect to the variable z, which was actually one of the input variables. So to do that, what we can do is we can first note that, well, the output value of the function was f is equal to some value q, that intermediate value, multiplied by z. So if you recall from calculus, the partial derivative of this expression with respect to z is just going to be the value that is currently residing in q. That's just like the definition of a derivative for this multiplication operation. All right, so we can say that df dz is equal to q. And so given that we've already computed our forward pass and we've stored that in the computational graph with the intermediate variable q, we can then directly copy that into our resulting gradient for df dz. And you can see now that we've put 3 as the value for df dz. Okay, so we've started to work through our computational graph in the backward pass, and let's kind of move forward. So now we get to this one, which, let's see, is still relatively simple. So if we want to now calculate the derivative of the function with respect to the intermediate value q, so what we want is df dq, we can use that same idea. So if we go back to our function f, we can say, okay, f as output is the result of q multiplied by z. So the derivative of that function with respect to q is now going to be the value that is currently residing in z, which we can see in our computational graph is -4. So now we'll just say, okay, df dq is going to be assigned the value of z based on the definition of a derivative for a multiplication. And then we can store that now in our computational graph for df dq. And now what we get to is a slightly more interesting, slightly more complex example. So if we now want, let's say, to calculate the 2 remaining derivatives, so the derivative of the function f with respect to y, and then separately the derivative of the function f with respect to x, now we're going to have to do something a little bit harder, right? So in particular, what we're going to use is the chain rule. So what's shown here is an application of the chain rule to compute this, this derivative. So what the chain rule is saying is, okay, if you want to calculate the derivative of some function with respect to a variable where that function is actually using some intermediate operation internally, you can calculate it by applying, let's say, the derivative of the function with respect to that intermediate variable, so df dq, multiplied by the derivative of that intermediate variable q with respect to the final, or like the input variable y, which you're interested in. And so derivatives are representing rates of change of one variable with respect to another. So df dy, what that's representing is what's the rate of change of the value f as you were to slightly change the value of y. So one way to kind of intuitively understand the chain rule is it's saying, okay, the rate of change of f with respect to y is really the rate of change of f with respect to some intermediate variable q multiplied by the rate of change of that intermediate variable q with respect to the input variable y. So for the purposes of backpropagation, what we'll do is we're going to refer to these different derivatives, or when we move to vector valued functions, these gradients with the terminology shown on this slide. So what we'll do is we'll say that the downstream gradient is the one that we're interested in calculating, and that downstream gradient is going to be a function of a local gradient, which is the gradient of just this sort of like local operation within the computational graph, multiplied by some upstream gradient which has been calculated for us already. So in this case, the upstream gradient is -4, so that's df dq, and then the local gradient is going to be calculated based on the specific algebraic operation at this portion of the graph. So this is just some terminology that's used within the deep learning community. Okay, so in this case, so now if we want to actually apply the chain rule in this case and calculate our final downstream gradient, what we'll do is we'll now consider what is the local gradient at this node in the graph. So at this node in the graph, what it was doing is it was performing an addition operation. So q was equal to x plus y. So the derivative of that value q with respect to the input variable y is just going to be +1 based on the definition of a derivative for an addition operation. So now what we can do is we have all the pieces we need to calculate our final downstream gradient at this portion, right? So we'll take -4, which was the upstream gradient, multiply it by that +1, which was the local gradient, and then we arrive at our final downstream gradient of -4. We'll do the same exact process for the final gradient that we're interested in calculating. So what we'll do is we'll say, okay, going back to our intermediate variable q, which is where we are within the computational graph where we're operating, the partial derivative of this value q with respect to x is also going to be +1 because it's just an addition operation. So we'll take our upstream gradient at this node, which was -4, multiply it by our local gradient, which was calculated to be +1 here, right? And then we get, once again, a value of -4 for the downstream gradient, but in this case, it's the derivative of f with respect to x. So I know we stepped through that in like maybe excruciating detail, but the reason why it's useful to do that is because we're starting to build some intuition about how this algorithm actually operates for a given computational graph. And hopefully what you're starting to get a sense of is if you wanted to implement this algorithm, all of the individual operations that you would have to define in order for your algorithm to go both through the forward pass and then also each of those backward passes. So at a high level, though, one way you can think about the backpropagation algorithm is it's a way to compute all the values you would need such that you could apply the chain rule automatically to compute all the gradients of the particular loss that we're going to be looking at with respect to all the inputs, but also with respect to all of the intermediate values within your computational graph. Okay, so one really, really nice property of the backpropagation algorithm, and part of why it's very computationally efficient, is because it's defined, like all the operations that we just looked at are defined locally based on specific portions of the graph. So in stark contrast to what you would be doing by hand deriving all of those gradients, the backpropagation algorithm can be defined not with respect to like an entire network, but you can define backpropagation in terms of just local operations at each node within a computational graph abstractly. So what that kind of looks like, we'll look at this example where if you were to define, let's say, the operations we just looked at on one particular node, this function f, let's say that this function f takes in two scalars, so x and y, and will output then a single scalar z. So the process that we just looked at, I mean, this is slightly moving towards generalizing the algorithm, but the process we just looked at is, first what we would do is we would assume that for this portion of the graph, there's going to be some upstream gradient that's already been calculated for us, right? So that upstream gradient would represent, in the case of training neural networks, the partial derivative of some loss, which is a scalar loss, with respect to this output of the function z. So this, from the standpoint of the algorithm looking at this specific portion of the computational graph, this value has already been calculated. So any instructions that we want to define for the algorithm at this portion of the graph can ignore all the compute that went into computing this upstream gradient. From its standpoint, it already exists and is being passed in as a parameter to our like backpropagation operations at this step. So at that point, let's say so we have this input to this node coming from the upstream gradient. The work then of backpropagation is really to calculate these local gradients, right? So in this case, it's to calculate how does the output value z change with respect to the input x? So that's dz dx, this first local gradient at the top. And then also, how does the output value z change with respect to the input value y, which is dz dy, the second local gradient. And if our backpropagation algorithm can compute these two values locally, then it knows how to produce the downstream gradients as just applying the chain rule, right? So just multiplying dz dx by dl dz to produce our downstream gradient for dl dx up here, and then also applying the chain rule a second time to produce the second outstream gradient, which in this case is dl dy. So the nice part about this is you can imagine if we could just define in algorithmic form what these two, or like how to compute the local gradients for this arbitrary function f, we could then expand our usage of the backpropagation algorithm to maybe like a very, very large scale computational graph where the actual implementation, though, is ignoring what the graph structure looks like from a global perspective, right? It's just defining an algorithm that uses local information that can then extend to some global, more complicated graph. And so that's really a nice property of backpropagation. In addition, because of this local property, one of the other benefits is that you can vectorize these functions and potentially parallelize them, like on GPU processors or maybe some other form of compute hardware outside of a CPU. So you can get a lot of speed up, right? So you can imagine if in parallel, if we had some graph that could maybe be updated like in parallel where the values weren't interdependent, perhaps, then we could maybe get some computational efficiency gains by computing local gradients of different nodes at the same time. So that's like another nice benefit of this local properties of backpropagation is that it's nice from the standpoint of implementing the algorithm in that you can just focus on what is available at a specific portion in the graph, but it's also nice because you can start to find optimizations that would let your implementation speed up and benefit from hardware acceleration. So I'll pause for a second and see if anybody has any questions on what we've kind of stepped through so far. Yeah, so the question was, so this dl dx and dl dy, so these downstream gradients that we're getting, are we using those to update the loss? Right, that was the question? Yeah, so what we're going to be using these downstream gradients for is within like a gradient descent algorithm, we'll use those as directions in the space of parameters to move such that we would minimize the loss. So in particular, like a brief recap from gradient descent was, if you take a step in the negative direction of a gradient, so if you move the weight vectors, so in this case, it's like if you were to change the value, like the input value of this function x, according to the negative direction of this gradient, you will be, if your step size is small enough, you'll ensure that the loss function decreases. That's gradient descent. That's how we'll use these gradients within gradient descent. So the question was, usually backpropagation is used to update the weights for like a neural network. That's true, but it's backpropagation in addition to some optimization function. Backpropagation itself is just being used to calculate the gradients. And then the gradients we can use in some gradient descent-based algorithm to actually update the weights. But within backpropagation, we're not changing like the value of x, which would be potentially a weight. We're just calculating the gradient of the loss with respect to x. And then the next step, or if you like go back to like one lecture, then that's how we would use the gradients to actually perform an update step. Yeah. Yeah. very interesting question. So the question for those online was, we talked, I think it was maybe last lecture, maybe two lectures ago, about how ReLU activation has some nice properties for the purposes of serving as a nonlinear activation function within neural networks. And we mentioned how ReLU is the default activation function within most neural networks that you'll see. And then the second part of the question was, given that we've seen how the benefits of ReLU, there's also sort of a baked-in observation that ReLU is non-differentiable because it has like a corner at x equals 0, where it transitions from being constantly 0 for any negative values on the domain to then being linear. Yes, ReLU is not differentiable in that definition. There's a topic called subgradients, which lets you make a non-differentiable function differentiable in some cases. So it's kind of outside the scope of today's lecture, but if you're interested in that, look up subgradients of ReLU. But essentially, if you define the gradient at that one non-differentiable point, then you can still apply backpropagation with ReLU, is the answer. Thank you for that. That's a very interesting question. Okay. Any other questions before we move on? Okay. All right. So let's look now at another more complex example, and let's consider this function that's given on the slide. So first what we'll do is we'll describe this function in terms of the computational graph, and then step through the backpropagation algorithm that's being applied to this particular function. Once again, to build some intuition about how backpropagation works, and hopefully now to start to see how the actual operations that we just looked at generalize across graph structures. So in this case, if we write out what the computational graph for this function is, what we get is what's shown here. So this function we could actually think about as being sort of a two-dimensional classifier. So if we look at the internals of the function, what we have is we have some x as input and some w as input. These are both going to be two-dimensional based on the notations that we have here. So we can see we have w0 multiplied by x0 and w1 multiplied by x2, in addition to then what is essentially a bias w2. So that really is sort of a two-dimensional linear classifier. So we're getting closer now to looking at what a computational graph would look like for the linear classifiers we've talked about in some of the past lectures. So given those input values for x and w, we can see then those corresponding values showing up on the left-hand side of our computational graph. So we have w0, x0, w1, oh, my mouse is not there. W0, x0, w1, x1, and then w2, our bias. And then looking at what the operations are being performed, if we sort of step through, we can see that we have the w0 multiplied by x0 as this multiplication node. We have w1 multiplied by x1 as another multiplication node. So that's representing these two operations, like w0, x0, w1, x1. W2 then is added to the results of the summation of the output of those multiplications. So up to this portion in the computational graph where my cursor is just computing this inner portion of the exponentiation in the denominator. At that point then, we have like this, multiply the results of that addition by -1, take the exp of that result, add 1. So at this portion of the computational graph, we're almost done. We've computed at least what goes into the denominator. And then the final step, the final node, is just taking the 1 over that denominator. So what we just sort of walked through was the forward pass, right? So if we were going to actually compute using backpropagation what the output of this function is, we could calculate all of the intermediate values if we gave some instantiated values to the inputs, right? So if we just picked out some inputs for w0, x0, w1, x1, and w2, let's say it's the values that are shown on this on this left-hand portion of the graph. If you work through these operations, you'll arrive at an output value of 0.73 for those particular inputs. So backpropagation, right, in the first step is just going to go through the full function, all of the operations that are involved in that function, and compute the result. The more interesting part then is the backward pass, right, where we're trying to compute the gradients of the specific output of the function with respect to all of the inputs and the intermediate variables. So in this case, just as we saw in the last case, the first thing backpropagation is going to do is start with the base. So the base case is always the derivative of the output with respect to that same output, so it's 1. And then it gets more interesting, right? So the next step, if we're working backwards, is to first look at the function 1 over x. And so if we want to take the partial derivative of this operation 1 over x with respect to x, that's given by the local gradient. So the local gradient in this case is negative 1 over x squared. So if you remember some of the rules from calculus, that should look pretty familiar, right? So in this case, it's really like d dx of x to the negative 1. So you bring down the negative 1 and then subtract 1 from the numerator, and what you'll get is then what's shown here, or from the exponentiation term, you'll subtract negative 1 from the power. So if we want to calculate the resulting downstream gradient at this node, what we do is we take the upstream gradient, which was our base case of 1, and we multiply it by the local gradient, which is computed using this expression with the specific value of x at this node. So at this node, the value of x, as far as it's concerned locally, because it only has the backpropagation algorithm at this step will only have information shown within this kind of local orange box. So if you take negative 1 over x squared, where x is 1.37, and you multiply that by 1, you'll get negative 0.53. Question? Right. So the question was, are we responsible, or is backpropagation at this step of the algorithm responsible for knowing how to calculate the local gradient for this specific node in the graph? And the answer is yes. So when you actually go to implement backpropagation, generally what will happen is, like, if you dig into the internals of PyTorch, there'll be a set of operations for which the local gradient computation is defined. And so if you then go and try and define some new algebraic expression that doesn't have a local gradient update, you shouldn't expect to be able to run backpropagation on that new algebraic expression. What you would first have to do is define how do you compute the local gradient with respect to this new operation that you've created before you could expect to include it within some backpropagation package, like some library that applies backpropagation. Yeah. Okay, so this step, so once again, so you plug in the value of x into the local gradient term, and then you multiply that by your upstream gradient to arrive at your downstream gradient for this node, and then you keep working backwards, right? So in this case now, if we look at this final +1 operation, which was within the denominator, once again, backpropagation can just kind of focus in on the local information. So it can take the upstream gradient, which we just calculated, it can then multiply that upstream gradient by the local gradient. So the local gradient for this function x plus 1 is going to be just a constant 1. So we're just essentially carrying back that upstream gradient as our downstream gradient of negative 0.53. And you can keep going through this process. So the x function is a little bit more interesting in that the derivative of x, which is e to the x, is just e to the x. So if you take e to the power of negative 1, because our x value, our input value for this portion of the computational graph is negative 1, and you multiply that by the negative 0.53 upstream gradient, you'll get negative 0.2. I think it's really negative 0.198, something. It's a floating point, so it keeps going. But then you would keep going backward with this process all the way through the computational graph. So if we go one step further, we have this negative 1 multiplied by x. So the derivative of this local function, negative 1 times x with respect to x, is going to be negative 1. So this is just going to, so if we want to calculate the downstream gradient, we'll take our upstream gradient, which was negative 0.2, multiply it by this local gradient of negative 1, and we now have positive 0.2 as our downstream gradient. And then it gets slightly more interesting. We have, I guess, okay, this node's not super interesting. So these are two additions that we're looking at. There's x plus y, so we want to know the local gradient with respect to x, which is going to be 1 because it's an addition, or the local gradient with respect to y, which is also 1 because it's an addition. So once again, at this node, we're just carrying our upstream gradient of 0.2 into the downstream gradients, so 0.2 at this intermediate node, and then 0.2 for this input node. And now it gets, okay, another addition node, so it's sort of the same process. And then for the final multiplication nodes, the difference is that the local gradient now depends on the inputs respectively. So the local gradient with respect to the input, so d dx of x times y is the value of y, and d dy of x times y is the value of x, which again were the inputs. So So to calculate the downstream gradients at these final nodes, what you would do is you would take your upstream gradient, which we've calculated here as 0.2 for this portion of the computational graph. We would multiply it, in this case, by the local gradient for let's see. So we multiply by the local gradient for, let's say, the W0 term. So the local gradient for the W0 term, so dW0 with respect to W0 multiplied by X0 is whatever the value of X0 is. So in this case, X0 was -1. So we'll multiply our local gradient of -1 by our upstream gradient of 0.2 to arrive at our downstream gradient at this node of -0.2. And then you do the same thing to calculate the downstream gradient in the other direction. So you take your upstream gradient of 0.2 and multiply it by the derivative of W0 times X0 with respect to X0, which is W0. So it's 0.2 multiplied by 2.0, and it's 0.39 if this 0.2 has been rounded. So that's just like a slight rounding error. And then the same process using the partial derivatives would be applied to that final multiplication node in your computational graph. And at that point, backpropagation would stop because it's covered all of the nodes within the graph, and you'd now have calculated all of the gradients for this computational graph. So you have the gradient of the output with respect to all of those intermediate variables and also the original input variables. Okay, so once again, we sort of stepped through this algorithm to a very explicit detail, right? So we've looked at every single step that would be required for this given computational graph. And one observation that we can start to make is that within this specific computational graph, we've actually seen a function which is used very commonly within neural networks, which is called the sigmoid. So the combination of these nodes within this computational graph actually represents the sigmoid function. So if we define sigmoid as 1 over 1 plus e to the negative x, we can see that this portion of the computational graph represents that expression. So one interesting observation we can make is that what we might want to do if we're going to be implementing a backpropagation library is we might want to actually abstract away the computational graph for sigmoid and the local gradient updates that would be calculated for sigmoid, so that if multiple developers wanted to use sigmoid within their neural network, which many will do, the sigmoid is kind of a common activation function you might see. By abstracting away the sigmoid graph and generalizing it, we could then define a sigmoid layer so that others could just implement the sigmoid layer instead of having to implement these lower level operations of like division and e to the negative x. So that's one motivation of potentially generalizing elements of computational graphs that are common, is you can maybe build in some optimization there and potentially some nice APIs for the developers at the higher level. Let's see. So one example of what you might do if you wanted to implement, let's say, like a sigmoid layer that's kind of unique to your backpropagation library. So instead of defining local gradient updates with respect to all of these lower level operations, what you could instead do is you could derive, so it's like a little bit of a pain here, but it'll come potentially with some computational benefits. You could derive on paper the local update for the overall sigmoid function. And so if you work it out, I'll leave it as an exercise, but if you work out what the derivative of the sigmoid function is with respect to its input, this is kind of a very abbreviated version of that derivation, but you'll find that it's 1 minus the value of that sigmoid function given the input multiplied by the sigmoid function given the input. And so now if you wanted to, you could implement a sort of sigmoid layer and then a local gradient update using this equation, which then the users of your API could use instead of having to define local gradient updates for all of these lower level operations that get chained together. So it's sort of, the point that I'm trying to make here is that when you're implementing backpropagation in practice, you can choose what level of abstraction you want. If you want to go down to the absolute lowest level, just in terms of like the basic algebraic operations, you can do that. But it might have some benefits for the purposes of actually designing an API that you would choose a slightly higher level of abstraction just for the users of your library. And so just to show that this actually is that will end up with the same values if you work through the calculation of according to our derivative here versus what we had worked on using the lower level algebraic functions, you'll find it's actually the same results. So like 1 minus the sigmoid function given the input x. So in this case, the sigmoid function output was 0.73. So 1 minus 0.73 multiplied by 0.73 should be our local gradient for this entire, for all of these 4 operations shown in the blue box here. So given that local gradient multiplied by the upstream gradient, which was 1.0, results in 0.2, which was the exact same downstream gradient we got when we went through the lower level backpropagation steps. Take another water. All right. So kind of on a similar theme, one thing that's useful maybe to start thinking about is how certain patterns can start to arise in the flow of gradients depending on the specific algebraic functions that we're trying to calculate gradients with respect to. So in the case of an addition operation, what you'll find is that the gradient will, if you were, like during backpropagation, the gradient from your upstream is essentially getting sort of redistributed to all of the downstreams. So, and the result of that is because when you calculate that local gradient with respect to your inputs, it's 1 in both cases. So what you're doing is that 1 multiplied by your upstream to produce all of your downstreams is like it's just kind of copying the upstream into all of the downstreams. So in this case, you can see, I mean, we just sort of picked out values, but let's say that our upstream gradient was 2, and we're computing through backpropagation through an addition operation. That value of 2 for the upstream gets copied as the downstream for both branches. Another kind of common operation you might see is like a copy. So if you were to copy the input, let's say value of x, and sort of copy it into 2 downstream branches, the results on the gradient side is that if you have multiple upstream branches coming back through this copy, their gradients will be combined through addition to produce the downstream gradient. So in this sense, the addition gate and the copy gate are sort of like duals of one another. So they're sort of, in the forward and the backward, they're sort of applying the inverse effects. Yeah. So another couple of common ones that you'll see, so like the multiplication gate, which we've seen a number of times in the examples. What that is essentially doing is sort of what we call like this swap multiplier. So what we mean by that is we take our upstream gradient and then we're going to multiply it. So to produce a specific downstream gradient, so let's say to produce the downstream gradient along this first branch, we'll take our upstream gradient and multiply that by the other branch's input, right? So we'll take 5 and multiply it by 3, which was the second branch's input, to produce the downstream gradient for the first branch. And then we do the same, but just flip the branches for the second branch. And then another one which you've started working with in project 1, for example, is the max gate. So let's say we have 2 inputs coming into just an element-wise max operation. In that case, what you're going to do is during the backpropagation, the gradient is only going to, the downstream gradient will only be affected for the branch of input which was the max. So in this case, let's say that we're taking the max between 4 and 5 to produce 5, right? 5 is greater than 4. So when we go through the backward pass, let's say we have some upstream gradient calculated, which is 9. That 9 is only going to be passed along the branch that corresponded to the chosen max value. And for the other branch, there is no gradient. So the way to interpret that is that if we were to slightly change the value of 4, right, like by an infinitesimally small amount, we would not expect the output of this function to change at all. And so that's why, correspondingly, the gradient for the output with respect to that smaller input is 0. Question? Why we have the gradients in the copy gate? Yeah. So in the copy gate, so in the copy gate, one way to think about it is, so and again, for all of these examples, one thing to keep in mind is that we're always assuming the gradient is with respect to a scalar loss. So essentially, eventually, all of the outputs are going to come down to one scalar value as the output of our function. So in the case of a copy gate, if we were to slightly change this input value of 7 by an infinitesimally small amount, what effect is it going to have on the final output? Well, in this case, because that input 7 was sort of duplicated, it's going to have that it's going to have an effect that goes down both branches in the forward direction. And so correspondingly, in the backward direction, we want to accumulate all of the gradients that it's sort of responsible for back into this first branch. Is it distributive multiplication? What do you mean by distributive multiplication? Yeah, so I suppose we're kind of getting, yeah, so you could implement distribution using copies. So yes, so you could expand out a multiplication over an addition by copying the term on the left by distributing it out like you're saying. So yeah, that would be one case. Or just using the same input in two different places. That as well, yeah, which is also kind of distributing, right, copying the data in multiple. So anytime you sort of copy one data element into multiple places, you could think about that as an application of the copy gate, yeah. Okay, that's a really interesting question. So in the max gate, if both elements are 5, then when you calculate the gradient, will the 9 be distributed to both branches? So in other words, like let's say that the input was 5 on the first branch and 5 on the second branch. The max is still 5, but for the purposes of defining backpropagation, that's actually a case where you have to define a subgradient because technically the max function is not necessarily differentiable. So it would depend on how you implement it, is the answer. Yeah. So, and that, yeah. So look into, so yes, your understanding is correct. So that's kind of, that depends, so the way we define derivatives is with respect to an infinitesimally small change. So, the definition of derivative is kind of ignoring the case you're sort of suggesting, where you're picking you're picking a finite value to define that change, and to try and find an edge case. And I'm sort of saying, like the definition of a derivative never picks a finite value for the step size. It is an infinitesimally small, like with respect to an infinitesimally small step size. So it's defining rates of change and not actual change, like not an actual step. So yeah, so the question, by the way, for those online was, in the case of the max operation, let's say that the two inputs are close enough that even a very small amount of noise would actually cause one of them to be greater than the other and correspondingly having a change in the output of the max function. And what I'm kind of proposing here is that the definition of a derivative is ignorant of that scenario, because the derivative is defined as the rate of change given some infinitesimally small change of the input. And so your choice of you have to be picking some finite step size of a change of noise for that case to actually occur in practice, which the derivative is not, yeah, it's just like, it's talking about different things. Like the derivative is saying a rate of change with respect to an infinitesimally small step size, and you're saying what's the rate of change with a finite value step size? So it's yeah, and so the question was sort of coming back to the case of, like, let's say the max gate where the two inputs are the same, like 5 and 5. Maybe instead of duplicating the gradient, you could just carry a single branch, kind of ignore that there were two inputs to the max and treat it like there was just a single carry forward. That would be a way of implementing this case of a non-differentiable function. So you're sort of implicitly choosing a subgradient by that implementation. But So for the purpose of like our lecture here, the only thing to note about a subgradient is it lets you apply backpropagation on functions that are non-differentiable. That's sort of outside the scope of what for this class we need to worry about. Like we're not going to be worried. Like that kind of gets more into pure calculus about whether or not subgradients are real. So for now though, let's just take it that we can for some functions which we're going to be interested in, like max and like ReLU, which by the textbook definition are not differentiable, we can still apply backpropagation using some technique which we'll sort of hand wave over as a subgradient. And if you're interested in further reading on that, we can talk at office hours, or probably like a pure calculus, like vector valued calculus class is better. Okay. Good questions. I love the questions. Okay. So we've looked at now a couple of examples in a large amount of detail with how backpropagation goes forward and backward. So now let's start to think about if we were to actually try implementing these steps that we've been talking over in code, how would we do it? So for the case of a forward pass, it's probably very intuitive. So what you would do is you would, according to the order of operations defined in your algebraic notation, you would then have operations defined in code. So for this particular example, which is the same one we looked at, where we're just abstracting away some of those final algebraic nodes within the graph as just a single sigmoid function, we could implement this according to these 5 lines of code here, right? So the first thing that we're doing is we're multiplying W0 by X0, then in a separate intermediate variable, W1 times X1. So that's this portion of the computational graph up here, those 2 multiplications. Then we add those 2 intermediate variables to form this node. Then finally, our final intermediate variable, S3, which is the sum of that S2 plus W2, so that's here. And then we apply sigmoid, right? So there's a forward pass. If we now wanted to try and implement a backward pass, we could imagine writing out all of those steps that we talked through just line by line in code, working importantly from the backward, in the backward direction. So working first from our base case, right? So we have this base case where we're setting the gradient of the loss with respect to itself as 1.0. And then for every single node within the graph, we're going to have some corresponding code to go along with it. So in this case, you can see, so like for our call to the sigmoid during the forward pass, we also have an update which is going to calculate our downstream gradient, which is the gradient of the loss with respect to our intermediate S3. So moving backward again, you can sort of define, in this case, it's going to be 2 separate gradients, one for the gradient of the loss with respect to W2 and one for the gradient of the loss with respect to S2, based on the fact that there were 2 branches, right? So 2 downstream gradients that are going to have to be calculated for this specific node from the forward pass. And so this same kind of idea extends. So we'll call this, for the sake of this class, the sort of flat gradient code, right? Where you're sort of doing these linear operations forward and then linear operations backward based on the function. And so I'll point out that for project 1 and at least a part of project 2, this is how you should imagine implementing, this is how you should implement your gradients. So just as like a snippet of code, this was taken from the SVM loss function for the code that you should be implementing or have implemented. So the way that you should go about implementing this is using this kind of flat approach, where in the forward pass, which is what's shown on the left here, you'll have, like maybe first you'll calculate the scores, and then you'll calculate what the max score was, and then like the margin, and then the data loss, and the regularization loss, and then add them together. And then on the backward side, you should correspondingly then differentiate backwards according to those same steps. So one takeaway from the discussion that we've had when you go to implement this is that the more granular you define your intermediate variables on the forward side will correspondingly affect how granular, and to some extent I would say how easy, the individual gradient calculations on the backward pass will be. So if you feel comfortable deriving things on paper, maybe you can make some abstractions on the forward pass. But if you're less comfortable with deriving the gradients on paper, then it's probably better to, during the forward pass, to have many intermediate variables so that on the backward pass, your backward steps through all of those intermediate variables are simpler gradients. Yep. Okay. So Okay, so then a note, and this kind of came up based on an earlier question, but in practice, when you start looking at machine learning libraries like TensorFlow and PyTorch, in practice, they implement these algorithms for you. So for the purposes of learning, we're going to be implementing backpropagation for projects 1 and projects 2. But in the case of practice, when you go to actually start using state-of-the-art neural networks or defining state-of-the-art neural networks, generally it would be a huge waste of time to redefine backpropagation because there's already highly optimized implementations for you. And so generally speaking, how these implementations will work is based kind of roughly on the pseudocode that's shown here. So they will actually construct, usually it's implicitly, but they will actually construct a computational graph within the code based on your definition of a neural network. So what they'll have is, for example, what's shown here on this in this pseudocode, where given some like abstract class of a computational graph, they'll assume that there's going to be a forward pass for that computational graph and also a backward pass for that computational graph, where during the forward pass, they're calculating maybe some intermediate variables, right? And then finally the final output, like a loss. And then during the backward pass, they're going to go back through all of the individual nodes in the correct order to calculate the intermediate gradients and the final gradients with respect to the inputs. So if you start digging into the PyTorch library, you'll actually find this. So here's an example of some code that using the PyTorch AutoGrad API would actually set up the forward and backward pass for the multiply function, which we've been talking about. So if we have some scalar inputs, x and y, for our multiplication function, PyTorch has this context, CTX, where it will store the upstream gradients for you. Right, so what we're doing here in this definition is we're defining just the local abstract algebraic node for multiplication, right? So we're ignoring like the rest of the graph. So what this context gives us are all of the values which we might need based on upstream from other parts of the graph to calculate the gradients for the inputs of just this one multiplication node. So during the forward pass, you can see we do our scalar multiplication, we'll return the final output, and then during the backward pass, we'll use the context that we stored during the forward pass of storing x and y to calculate the gradients that will be used for the downstream nodes in the graph. So one reason why some knowledge of this is useful is if you go to, like, let's say that you're working on a research project and you define some really interesting new layer that no one else has thought of, and this is actually fairly common. Before you can actually embed it within PyTorch, right? So maybe you just want to use like standard 2D convolutions in addition to your new fancy layer. Before you can actually implement it, you have to define a forward and a backward pass for that new layer. And so in practice, having some knowledge of these APIs is useful for the purposes of extending them to new algebraic functions. Okay, so far we've been talking just about backpropagation with scalars, but as we've been seeing, for the purposes of like image classification and for a lot of the perception data that our robots have access to, we're going to have to work with vector valued functions. So how does backpropagation extend to the more complex vector valued functions? So what we've looked at so far, right, was this case in notation. So we had some scalar input x, some scalar input y, which y in this notation is our output of the function. And we were looking at these derivatives, right? So the derivative of y with respect to x, which is also just a single scalar. So it's from the real number line. And so what this derivative measures is if x changes by an infinitesimally small amount, how will y change in response? For vector valued functions, things get a little bit more complex. So let's say that we have a function y, which is still a scalar output function, but the input now is a vector, right? So x is this n-dimensional value of real numbers, and then the output of some function of x, y, is just a single scalar. Now what we're going to do is we're going to refer to these derivatives as gradients. So up to this point, I've been using derivatives and gradients kind of interchangeably. And for most of deep learning terminology, you'll see that kind of common. The reason why we treat them interchangeably is because we always are thinking about tensors, so we are always thinking about gradients. So in this case, so now what we're going to have are partial derivatives of the function, this scalar y, with respect to all of the individual inputs of x. So now what this gradient is actually a vector of the same size as x, because what it's measuring is for every single element of the input, so all x sub I, how would the single scalar output change if you were to slightly change just x sub I? So once again, so this gradient is the same size, it's the same dimension as your input x. Also, though, of note and of importance is to think about if we had a function which takes in an input vector x, so let's say an n-dimensional vector, and the output of the function is some other vector, in this case of dimension m. So for most of the neural networks which we'll be working with, this is really a more accurate description of what their domain and range is. It's going to be some multidimensional input and some multidimensional output. So in this case, the derivative is really referred to as the Jacobian, and that Jacobian is represented as a matrix. So what it measures is for every possible input variable, so we'll call those x sub I, how would one individual output variable, y sub j, change? So that's why we have a matrix. So you're measuring every possible kind of pairwise rate of change that could occur according to this specific function that we're considering. So once again, what those individual elements of the Jacobian measures is for each element of x, if it was changed by a small amount, how would just one element of the output, y sub j, change? Would it change by a lot or a little? Would it increase or decrease? That's what the Jacobian is measuring. So given this, let's look at how our view of backpropagation would change for the case of vectors. So we'll look at matrices after. So let's assume that we still are working kind of locally within our computational graph to simplify the discussion. Let's say that we have a function f, which takes in two vector-valued inputs. So we have x, which is some vector of dimension d sub x, and then we have some other vector input y, which is of dimension d sub y. So for these slides moving forward, all of the blue notation is describing some size change in either the inputs or the outputs or the sizes of the gradients from what we saw in the scalar case. So the output of this function is also a vector of size of dimension d sub z. So our loss, though, importantly, always for this class, our loss is going to be a scalar. So we don't have to worry about multidimensional losses. So if our loss is a scalar, one thing that the first thing we can observe is that our upstream gradient for this specific function is going to be the same dimension as the output of this function. So it's going to also be of dimension d sub z. And the way to think about that is because this upstream gradient is still measuring for every element of z, for which there are d sub z elements of z, how will the loss, the scalar loss, change? Internally, then, what we have are Jacobian matrices to define the local, what we were previously calling gradients, but in this case, the local Jacobians for this function. So the dz dx is now a matrix, a Jacobian matrix of size d sub x by d sub z. And because, once again, what that Jacobian is trying to represent is, according to this function, how does the output element, how does every individual output element within z change with respect to every single input element x, and then similar for the vector input of y. So then our final downstream gradients are going to be calculated using a matrix vector multiplication, where we take these local Jacobians and we multiply them by the upstream gradient. So the final output sizes then are the same shape or the same dimension as the input vectors were. So the upstream gradient along this x branch is of dimension d sub x, and the downstream gradient. And the downstream gradient along the y branch is of dimension d sub y, which was the same as the input vector y. So all of the other discussion, though, that we had on backpropagation extends naturally now to this case of vectors. So as long as we treat this as a matrix vector multiplication for calculating the downstream gradients, all of the other discussion still applies. Now, we do run into this challenge, which is we actually have to define what the Jacobian is for a given function, right? So instead of just defining scalar derivatives for those scalar valued functions, now we have to define Jacobians in order to apply backpropagation. So let's look at an example, and I'll try to kind of go through quickly based on time. So let's consider that we're going to do, that we want to define backpropagation for, and we want to define in particular the local Jacobian calculation for this element-wise max operation for the maximum either between 0 or the element at a particular position in the vector. So in other words, so for this case, so the max between this element 1 and 0 would be 1, right, because 1 is greater than 0. But then at this position, the max between -2 and 0 is 0. So element-wise, you would follow that same process for all of the input positions in your vector. So if we're trying to apply backpropagation, for this function, locally, we can assume that we have some upstream gradient given to us. So these are just some values that are sort of given to us. We can ignore how they were created. And so one thing to note is, right, so the shape of this upstream gradient is going to be the same shape as the output of our function. So once again, it's a 4×1 vector. Now, though, what we have to do is we have to define, if we want to calculate the downstream gradients, what the Jacobian of this function is for our input x. So in order to do that, in terms of sizes, right, we know that the size of this Jacobian will be 4×4 because it's going to be the same dimension. It's going to be the dimension of the input multiplied by the dimension of the output. So the input was 4×1, and the output was 4×1, so it would be 4×4 total. And the way to read this Jacobian is essentially element-wise what it's describing is how would the output at this specific row change if the input value at the corresponding column changed by a very small amount. So what we'll notice initially is that all of the off-diagonal terms are 0. What that's indicating is that the output at a specific position does not depend at all or ever on any of the values of the input that were not at the same like element-wise position. So that's why the off-diagonal terms are 0. Some of the diagonal terms we'll see are 1, and what that indicates is that the specific input value at that column of the input was greater than 0. So in this case, for example, like 1 was greater than 0, and it's at the first position of the input vector. So the first column at the first row will be 1. So in other words, like the output depended on the input for that. Some of the diagonal terms are 0, and those are corresponding to the cases where the input value was less than 0. So if we were to slightly change those input values, the output at those elements of the output matrix would not change at all, according to our definition of the derivative. So once you've defined this Jacobian, then, if we treat our downstream gradient calculation as just the matrix vector multiplication between this Jacobian matrix and our upstream gradient, then you can arrive at your downstream gradient and then keep moving on with backpropagation. So a couple of important notes, and I really need to move forward for time, is one takeaway we can have from this example is the Jacobian is extremely sparse. And for most operations that we're going to be using within neural networks, so for example, convolution operations, which we'll talk about in next lecture, the Jacobian is naturally going to be very, very sparse. One way to try and think about why the Jacobian might be sparse for many operations that we're thinking about is sort of the more sparse a Jacobian, to some extent, it's defining the fact that your functions, like your transformations, are kind of efficient. Like they're ignoring maybe a lot of the inputs to produce their outputs. And we would like that, right? We would sort of like our networks to focus on just the things that they need to focus on. The downside, though, is because the Jacobians are very, very sparse, storing these super sparse Jacobians in memory and then operating on these like maybe very large sparse Jacobians is going to be very inefficient during backpropagation. So generally, when in backpropagation implementations, what you'll find is that you'll never explicitly define a Jacobian as a full matrix. Instead, what you'll try and do is you'll use code to implicitly define the Jacobian. So our code, even in like in the SVM loss, for example, was setting up some of this implicit implementation for you in project 1. But in particular, what you might do in this case is before actually deciding to take that full matrix vector multiply, instead you'll have like an if statement. Like you'll have conditional control flow in your code for backpropagation that will dynamically decide based on the specific function that you're implementing, so in this case the max function, whether or not it should compute anything at all or maybe just return like 0 for some elements of the downstream gradient. So this will be much, much, much more efficient when we start dealing with very large Jacobian matrices. Okay, so quickly, very quickly, I'll mention that this discussion extends then to multidimensional, so beyond just vector valued input, but actually matrix value or tensor valued in the case of tensors. So all of our discussion of backpropagation extends. So in particular, like let's say that instead of having a vector valued input x and a vector valued input y, let's say we have a matrix of dimension d sub x by m sub x for x, and of dimension d sub y by m sub y for y. The corresponding output, let's say, is also a matrix of d sub z by m sub z. So because our loss is still a scalar, we know that our first upstream gradient is still going to be the same shape as the output of this function. So our dl dz is still dz by d sub z by m sub z. And within the function now, we still have local Jacobians, but their dimensionality is increased. So now what we have are actually four, like they're like matrices of more than just a 2D matrix. It's now a 4D matrix for each of them. So we could kind of imagine grouping the dimensions together. And because we're almost out of time, I'll leave some of the thinking about how it is we could group them together as an exercise. But the kind of short answer is, if you imagine just sort of flattening your input into a vector, a lot of the discussion, like all the discussion we've talked about, still extends. So if instead of treating these as actual matrices or tensors, you just imagine treating it as a very, very large vector, then the discussion of backpropagation still extends. So you could still have a matrix vector multiplication to produce your downstream gradients, and then a worked through example is left in the slides for how you could compute the downstream gradients for a matrix multiplication example. And the reason why this is kind of a useful example to work through is it's worth considering how it would be actually impossible to store in code these Jacobians. So just using like a very small set of dimensions, which is like, let's assume that our input is of dimension n being 64 with 4096 as the second dimension, which on the scale of even the networks we've already started working with, that's a fairly small input size for like maybe many images within a data set. And then if our weight matrix, which is W, let's say, is also of dimension D sub D by M, which is also, let's say, 64 by 4096. If you use floating point 32 numbers, the corresponding Jacobian will be 256 gigabytes. So like right off the bat, with like a very small network, we've seen how it's not possible to do this. So the implicit Jacobian is very important. So I'd recommend, working through this example as homework. And then the last thing I just want to talk about briefly. Okay, I'll cut off there. There's some summary also slides in the notes, which I'll leave. But with that, that's the end of today. I'll stick around to answer questions, and I'll see you on Thursday.